Hello and welcome to chapter 19, which is going to be on cosmology, or the study or theory of how the universe as a whole evolved and came into being. The universe consists of all matter, energy, and spacetime that we can ever detect or will ever be able to affect us. We use this definition because there may be matter and energy in other dimensions, or matter and energy which are moving away from us so quickly that their influence will never reach us. So far in this text, we have explored matter on size scales from atoms to superclusters of galaxy. We have also learned that the superclusters are all moving away from each other, implying that the universe is expanding. In this chapter, we take the observational evidence from the rest of the book and use it to explore the Big Bang theory of cosmology. Cosmology is the study of the large-scale structure and evolution of the universe. Einstein's general relativity predicted either an expansion or contraction of the universe, which contradicted Newton's ideal of an infinite and static universe. To make the universe static, Einstein added a cosmological constant to repulse and balance out gravity's attractive force. We also see cosmological redshift, which is taking an original wavelength, and as the universe expands out, the wavelength is stretched out and redshifted, meaning that it has a lower energy on a longer wavelength, which is going to account for a lot of the theories that we're going to talk about in this lecture. Shortly after World War II, the astrophysicists Ralph Alpher and George Gamow produced it at a fraction of a second, or proposed that a fraction of a second after the Big Bang, the universe was an incredibly hot black body, in excess of a lot, as heat is a measured of how many photons there are and how energetic they are. If the Big Bang occurred, the early universe must have been filled with intensely high energy electromagnetic radiation, i.e. gamma rays, which are photons, which are high energy. As the universe expanded, the cosmological redshift would have stretched these gamma rays to longer and longer wavelengths, so that most of the photons left over from the event should now be radio waves. Recall that photon energies decrease with the increasing wavelength. Because the early photons should be redshifted, the energy they each have should be decreasing. This energy is measured as heat, so the universe should be cooling off as it expands. Calculations indicate that if the universe began with a hot Big Bang, the remnants of that energy should still fill all space today, giving the entire universe a temperature only a few kelvins above absolute zero. This radiation is called the cosmic microwave background because the peak of its blackbody spectrum should lie in the microwave part of the radio spectrum. Detection of the cosmic microwave background is the principal reason why the Big Bang is accepted by astronomers as the correct cosmological theory. So if you look at a blackbody curve for T equals 2.726 Kelvin, the cosmic microwave background data fits this with remarkable accuracy. Where this data actually came from astronomers or from radio technicians who were just looking into the void, or trying to find radio signals, and were finding that there was a constant background in there of noise that they couldn't get rid of. We also find that the background is slightly warmer or blue shifted towards Leo, while it's slightly red shifted away from Leo or towards Aquarius, which means that we should be moving towards Leo. Isotropy is not limited to the blackbody radiation observed throughout the universe, but it is a useful knowledge that we should know. It is also found on sufficiently large scales when exploring the number of galaxies in different directions. Astronomers have counted the number of galaxies of different distances from us in a variety of directions. The number of galaxies stays roughly constant with respect to both distance and direction, allowing, as we saw before, for the distribution of most galaxies on the filamentary regions throughout the universe. Because of this universe uniformity with distance, we say that the universe is also homogeneous. Isotropy and homogeneity must be explained by any viable theory of cosmology, such as the Big Bang. There are four fundamental forces in physics. The electromagnetic force holds electrons in orbits around the nuclei and atoms, which allows normal matter to exist. However, over large volumes of space, the net effects of electromagnetism cancel out because a negative electric charge exists for every positive charge and a south magnetic pole exists for every north magnetic pole. Although gravity is the weakest of all forces, it is the only force whose effect is both infinite in extent and attractive for all matter and energy. These characteristics are why gravity determines the evolution and behavior of stars, the orbits of planets, the existence of galaxies, and many other large-scale phenomena. Nuclear forces extend over distances of less than about 10 to the negative 15 meter. The strong nuclear force holds protons and neutrons together, overcoming the electrostatic repulsion of the protons, and the weak nuclear force causes certain kinds of radioactive decay. Protons and neutrons are composed of quarks, which come in 6 flavors: up, down, strange, charm, top, bottom. What happens is that sufficiently high temperatures, the different forces begin to behave the same way. So grand uniform theories combine the electromagnetic, weak, and strong nuclear forces under high enough temperatures, like those of the Big Bang. And we also want to have the gravitational force combined, but we haven't been able to observe this, or haven't been able to come up with a unified theory that includes the gravitational force, but we do kind of assume that it did used to work alongside like the other forces, where initially all forces are believed to be the same at the Planck time of about 10 to with a temperature of about 10 to the 32nd Kelvin and a time of 10 to the negative 43 seconds. Gravity branches off, then the strong force, then the weak force from the electromagnetic force. So looking through the history of the universe, we can see how hot it was linearly through the time after the Big Bang. So you start at the Planck time, gravity separates out, strong force separates out, inflation begins at the inflationary epoch. Weakened electromagnetic forces separate, and then confinement of quarks, universe transparent to neutrinos, synthesis of primordial helium, universe transparent to photons, and now. Now, what is the inflationary state? I am going to say that this is something that isn't well understood. I asked somebody who did their PhD in astronomy rather than me, who did their master's in condensed matter, and about what the inflationary period was, and they did not know exactly, or they had no better explanation than the book has, which is just that initially a universe was in a high energy false vacuum. Energy it went towards a lower energy, more stable vacuum, and rapidly accumulated inflationary mass, and then the universe rolled back and forth around the true vacuum, eventually settling down into the state of minimal energy. And after inflation ended, the weakened electromagnetic forces separated, causing elementary particles, quarks, electrons, photons, neutrinos, and their antiparticles to form. Inflation early on also is our best guess for what smoothed out the universe and caused that isotropy, or constant no privileged directions or anything like that, that we said earlier in the lecture had to be true or had to be addressed in order to explain, for any cosmology to explain the universe and to be accepted. So what you see here is that on either side of the inflationary epoch, it's getting bigger. The universe was getting bigger at about the same rate. However, during the inflationary epoch, it gets bigger much, much faster. And this inflationary epoch is our explanation for why the universe is the way it is, rather than random explosions or random pressure in different directions, or energy being deposited in a certain direction by the Big Bang for no apparent reason, causing there to be privileged direction versus the isotropic universe that we actually see in reality. Around 10 to the negative 6 seconds, the universe cooled sufficiently that quarks would stick together. In the first second of the universe, photon collisions created a lot of pairs of particles, a particle and its antiparticle, but after the second, the particles and antiparticles collided back into high-energy photons. Maybe the symmetry slash amount of matter slash antimatter might have been broken by the weak force during this time. Because we see that there is a lot of matter in the universe, and if there were an equal amount of antimatter, then it would just annihilate and become photons again. But considering the weak force, we think that that might explain why there is more matter than antimatter in the universe. For about 30,000 years, energy density of photons dominated the gravitational effect, but as the photons redshifted to lower energies, they accounted for less of the energy density of the universe, whereas the matter energy density also was going down, but it was going down at a lower rate. So at this crossover, we went from radiation or energy-dominated gravity and an energy-dominated universe to a matter-dominated universe. This is also something to do with the era of ionization and recombination. So before recombination, temperatures were so high that electrons and protons could not combine to form hydrogen atoms. The universe was opaque, photons underwent collisions with electrons, matter and radiation were at the same temperature. However, after recombinations, temperatures became low enough for hydrogen atoms to form, the universe became transparent, collisions between photons and atoms became infrequent, and matter and radiation were no longer at the same temperature. Pairs of particles can spontaneously occur, as we said when we were talking about the evaporation energy of black holes, but during the inflationary period, they were stretched and caused areas of slightly higher temperature, pressure, and density, and sent out sound waves that formed filaments of matter, which became galaxies and bigger clusters slash superclusters by the compression and rarefaction of the space and matter in this area at this time in a way that we won't see because matter is not as densely packed at this point. But as that matter expanded, it became the galaxies and filaments that we would see nowadays. And according to these fitting parameters or curve fittings, the filaments and the distribution of matter in the filaments do correspond to waves in compression slash rarefaction that you might see from the spontaneous generation of two pairs of particles. There was also a shift from elliptical to spiral galaxies, where elliptical galaxies are red and dead, meaning that they're low energy and don't have dying stars and are what we see of the very early universe, which we can see by looking as far out as possible into the universe or into space around us. And the farther out we look, the more far back in time the light that we are seeing comes from. If stars form slowly enough, the gas surrounding them has time to settle into a flat disk, and it becomes a spiral or lenticular galaxy, meaning that these spiral and lenticular galaxies become more common as the universe calms down, and we see here that elliptical galaxies were very common initially, and then spiral galaxies are now. And if the birth rate is high, then an elliptical galaxy is created, and virtually all pregalactic gas is used up in the creation of stars. We also want to know the curvature of space, where if the universe is curved, light rays from opposite sides of a hotspot bend towards each other. If the universe is flat, light rays from opposite sides of a hotspot do not bend at all. And if the universe is open, the light rays from opposite sides of hot spots bend away from each other. And what we found is that they don't bend at all, which means that the parallel beams remain parallel as they go across the universe, and this indicates something about the energy of the universe. So the universe appears flat, but the universe only has about 27% of the required energy to make it so. Dark energy is unknown, but causes the universe to accelerate outwards. And dark energy is unknown in the same way that dark matter is unknown, but we do see the effects of dark energy on the acceleration of the expansion of the universe, where we would expect all matter to follow exactly the Hubble Limbaert, I believe it was, rule if we were non-accelerating, but matter does curve a little above that rule.